Dr. Mohammed, and this is a new video under Engineering Mathematics course. Today I'm going to talk about the reduced row echelon form. So I'm going to talk about this reduced row echelon form and how we can obtain this from any matrix. So let's proceed and go to the introduction of today's video. So first of all, we want to highlight why that we need the reduced row echelon form and what is the meaning of it. So we want to understand first what is the meaning of the reduced row echelon form. And also we want to understand why we need it in the first place. So we can say that it is needed for the solution of systems of linear equation. As you are going to see later, that when we are going to solve linear differential equations, we're going to find that we are going to be in great need for such reduced form. It will make the process for the solution of the linear equations going to make it much easier. So now we understand at least why we need it for the solution of linear equations. How to get this row echelon form, or the reduced form in brief, we are going to explain it and define it. So first of all, the definition. Whenever you look to this kind of matrix, as you can see it here, you're going to find that kind of feature or some features that is making it a little bit unique than other different matrices. For example, you're going to find that whenever that you look to the rows, from the left you're going to find one element, and before it there is zeros. So for example, row 1, there is one element which is 1 here. Row 2, there is another element which is non-zero element, we call it 1, and before it there is 0. And for the row 3, there is also another non-zero element, and fortunately it is 1 also, as you can see. Before it there is 0. And when we look to the last row, we're going to find that all the elements of this row are zeros. So there is no non-zeros here. Okay? So look to this form deeply, and then you are going to understand what we are going to talk about and what is the meaning of the reduced form or echelon form. The leading entry of a row, so we are going to make definition first for something called leading entry of a row of a matrix is its first non-zero, take care of this, it is non-zero element reading from the left to the right, which is the 1s here. So the leading entry for row number 1, it is this one, the first non-zero element. And here for row number 2, and here for row number 3. And we do not have any kind of leading entry for the last row because it is 0 row. It is 0 row. Okay. If all the elements of a row are 0, then this row has no leading entry, as we said, which is this one. Okay. So this means that we have leading entries here, and we do not have any leading entry for the last 0 row element or row in this matrix. Okay. Now let's go to the definition itself. Okay, let's go to the definition itself. And n by m, n it is the number of rows, m it is the number of columns. And n by m matrix A is in reduced row echelon. We call it like this, reduced row echelon form, if it satisfies the following conditions. So we have different conditions that we need to fulfill in order to say that this matrix is in a reduced form. Number 1, the leading entry of each non-zero row is 1. Okay, so now we can realize that if we have a matrix like this, so the leading entry, which is, we understand now what is the meaning of leading entry from the previous slide. This means that the leading entry for all the rows must be 1 in order to say that it is in the reduced form. Fortunately here we have this is 1 and this is 1 also here, 1, okay, and this is 0 row. If any row has its leading entry in column J, which is for example this leading entry, it is in column 1, right? Then all other elements of column J are zeros. And this is right. Look to the other elements in this column. We're going to find them 0, 0, 0. Also here, look to this. It is the leading entry in column number 2, and you can find that all of the other elements are zeros. Here, 1, all other elements are zeros. And then for the last row, it is 0 row, so there is no leading entry. So now the second requirement or condition is fulfilled. So we have two conditions now fulfilled for this matrix that qualify it to be a reduced row echelon form. If row I is a non-zero row, okay, so if we say that this is row I and it's non-zero, non-zero means that there are some elements are having non-zero values. If row I is non-zero row and row K is a zero row and row K is a zero zero row, means that it is this row. So if we say this is row I, for example, and this is row K, which is 0 row, then I must be less than K. Means that this row, it is row 1, right? But this row, it is row 4. So that's right, 1 is less than 4. So what about this one, this row? The same. This is non-zero row, and its I, it is 2. However, it is 2 less than 4, which is the rank of, not the rank, but it is the order of this row. And also here, it is this row, it is row 3, and it is less than row 4, which is 0. So this condition is fulfilled also in this matrix that we can see. This means what? We need always the 0 elements to be at the bottom. 0 element or 0 rows to be at the bottom of the matrix. If the leading entry of row R1 is in column C1, this means that, for example, here we have this leading entry in column 1. This is column 1, and this is column 2, 3, 4, 5, for example. So if our leading entry in column leading entry in column 1, for example, okay, and the leading entry of row 2 is in column C2, and the leading entry of the column leading entry of row 2, which is R2, in column which is C2, then, and R1 is less than R2, as we are saying here, this is R1, which is this is first row, which is R1, and this is R2, okay, then C1 must be less than C2. This means that this row should be less than this, this column should be less than this column. It means what? It means that we need all the leading entries to be the first non-zero element to be read from the left, okay, and it should have the row 1, for example, here, if it's for row 1, it should be in the column 1. And if the leading entry is in row 2, in this element here, then the column that is having this element should be exactly C1 should be less than C2. So if we have the two rows here, let me clean up this here. So here, if this is row 1, this is row 2. Row 1 equals to 1, row 2 equal to 2, right? Here we have C1, and here this is C2, right? So as long as the leading entry of row 1, which is 1, and R1 is less than R2, then it must be that C1 less than C2. Means that we need our leading entries always to be shifted to the left like this. Okay, so before it, if it's the leading entry here, and this is row 2, okay, then the column should be shifted also to be at least 2. Okay, that's the same for all of them. Okay, so actually these 4 conditions are fulfilled in this matrix, then it is in a reduced form. When a matrix satisfies these conditions, we will often shorten reduced row echelon form and simply say the matrix is reduced. This is what we are going to say. The matrix is reduced. That's it. Or in reduced form. We can say both of them. Okay? So that's the meaning of the reduced row echelon form for a matrix. 4 conditions need to be satisfied. Okay. Now, so actually for the first condition here, the meaning is that condition 1 of the definition means that if we look across any non-zero row from left to right, the first non-zero element we see is 1. That's right, here, as you can see here, that I highlighted here in yellow. And condition 2 means that if we stand at the leading entry 1 of any non-zero row, like this one, and look straight up or down that column, we see only zeros. That's right. If you look here, down, all of them zeros. Here, look to up or look down, zeros. Here, up and down, zeros. And then there is nothing else here. And condition 3 means that any row of zeros in the reduced matrix, must lie below all rows having non-zero elements. That's true. 0 rows are at the bottom of the matrix. That's what we are saying. 0 rows is going to be at the bottom of the matrix. And condition 4 means that the leading entries of a reduced matrix move downward from left to right as we look at the matrix. That's right. You can feel it and you can see it here. This is one leading, going to from left to right and going down like this. Okay, so this is the shape, and these are the meaning of the conditions that we have explained in the previous slide. Okay, now let's see what are the examples of the reduced form. Look to these 4 different types of matrices and let us tell whether they are reduced form or not. So the first thing is, for example, for this matrix, I have 1 here, leading entry, and this is non-zero. Okay, to the right of the entry, no problem, any number would be there. The problem always, whenever that I look to the leading entry, I should look to the left and look to down and look up. Okay, so now I'm looking here, this is leading entry 1, okay, and then look to the row number 2, looking here, all of them zeros, and then 1, that's okay, and then above it and down it there is 0, so it is okay, qualified to be reduced echelon form. Okay, let's have a look here. So here there is no 0 rows, only non-zero rows. Let's have a look here. The first row, this is 1 leading entry, so here it is 0, it's okay. And look down, all of them 0. Up, there is nothing, so it is okay here. Then look to the second row, all of them 0, 0, 0, and then this is the leading entry, okay. Look up, look down, 0, 0, so it is okay. Look to the last row, it is 0, 0, 0, 0. It is a 0 row, then it is okay. Then also this one qualified to be a reduced matrix. Let's go to another case. Here, first row, this is the leading entry, and it is 1. This is 0. All of, looking down, all of them 0. Okay, so row number 1 qualifies. Look to the row number 2. All of them zeros here, and we have a leading entry here. It is okay. Look above, look below, 0, 0, so it is okay. Row number 2 qualifies. And then row 3 and 4, as you can see, they what? Zeros. So they are okay because they are in the bottom of the matrix, then this is a reduced matrix or echelon form. Okay, let's have a look here. Now we are trained for this. We have 1 here, so it is okay. We have, and everything is 0 here. 1 here, above 0, down 0, it's okay. For this row, we have this is leading entry, 1. Everything is 0 on the left, above 0, down 0, it is okay. The last row, it is 0. So all the rows are qualifying it to be the 4 conditions that we have explained before. So it is qualified to be a reduced matrix in a reduced matrix form. Okay, now let's go to another form of a matrix that is not reduced form. Okay, for example, if we have a C matrix, as you can see here, and it has these 3 rows, so this matrix is not reduced. Okay, it is not reduced. However, we can change it to be in a reduced form. Okay, we can make a sequence of elementary row operations. We can transform C to a reduced matrix based on this. For example, look to this. Do you remember the row operations? For example, look to this 2. If I multiplied row 1 by half, for example, what will happen for the first row? It is going to be, it's here 1, and then this is going to be 0, and then we're going to be half here, right? This means what? Here, this is 1. And fortunately, we have 0 here, right? So this is 0 here already, but we have 2 here, okay? So actually, this is 1, which is leading entry for row 1, and we have 0 in the second row when we look down, and we have 2 here. So we want to get rid of this 2 and make it 0, right? Okay. Okay, so in this case, we are going to make another row operation, which is going to make this elementary row operation. We're going to make this element to be 0. Yes, we can do what you are saying now, that we can, for example, we can multiply this by -2 and add this multiplication to row 3. So multiplying row 1 by -2 and add it to row 3, we are going to have this element to be 0, right? Okay, we're going to make the detailed one shortly, in a minute. So first, if the matrix had 1 or more 0 rows, so whenever that you look to any matrix and you see some rows to be 0, we would interchange rows to place these at the bottom of the new matrix. So if we have some zeros, for example, then always make interchanging and put the 0 rows at the bottom. Okay? So in our example, this matrix does not have any 0 rows. Okay? So we're not going to change. So we're not going to interchange anything. Okay? But if we assume that there was like zeros, for example, let's assume that, not here, let's assume that we have this row to be zeros, for example. Then the first thing to do is to move this row down and to bring this row up, okay? That's it. So this is the first thing that you should think about, which is the 0 rows. Okay, now let's go deeper into this C, okay? So in view of condition 4 of the definition, start at the upper left corner. We start always with the upper left corner. Multiply row 1 by half, as we said. So row 1 is going to be multiplied by half, as we mentioned before. Then we are going to have 1, 0, and half here to obtain a matrix having a leading entry of 1 in row 1. That's very nice. Then the second way, or the second next step, is to get zeros below 1. So we need to look down to find all of them zeros. So in the position under this one, okay, under this one, we need to have all the elements to be 0. Add -2 times row 1 to row 3. That's right, -2. I'm going to multiply it by row 2, okay? 2 times row 1, sorry, we're going to multiply 2 times row 1 and add it to row 3 and put it in row 3. Okay, so if you are going to make this minus 2 times 1 plus 2, it gives us what? Let's work on this. Minus 2 times 1 plus 2 equals to 0. And minus 2 times 0, it is 0. Adding to minus 2, so it is going to be minus 2. And minus 2 times half, it is going to be minus 1 plus 5, it is going to be 4. Right? So now we have this leading entry for the first row is 1 and the remaining are 0. I mean that in the same column. So now first row is okay for us. Now let's go to the second row. We have here, this is 0 and this is good. Now we want to think about this, which is minus 4. We want to change it to be 1. Right? Okay, so let's go and try to work to make this minus 4, we want it to be 1. How we are going to do so? It is easy. Using the row that already qualified to be in a reduced matrix, which is this one. Okay, now look across row 2 of the last matrix. The leading entry is minus 4, so divide this row by minus 4. Divided by minus 4. We wanted this to be 1. So simply we are going to multiply by 1 over minus 4. So it would give us 1 here. It would give us 1 here. Okay? So this means that minus 4 times 1 over minus 4, it is going to give us 1. Of course, 0, it will be the same. 0 will be the same. Minus 4 times 1 over minus 4, it is 1. And 6 times 1 over minus 4, it would give us minus 3 over 2. Okay, so now the second row qualifies to be in reduced form. So we have row 1 and row 2 now. Okay, now look to this matrix and look to the row 3. We want this minus 2 to be exactly to be 0, because here this is 1. So whenever we look up, there is 0, and whenever we look down, there should be 0 here. So minus 2 should be 0. How we can get this 0? Actually, if you look here, we can multiply this row by 2 and add it to row 3, right? So we're going to multiply row 2 by 2 and add it to row 3, right? So we want zeros in this. So add 2 times row 2 to row 3, as you can see here. So this is minus 2. So we're going to multiply here 2 times row 2, which is 2. So 2 times 0 plus 0, it is 0. 2 times 1 minus 2, it is 0. And then 2 times minus 3 over 2 is going to be minus 3 plus 4 is going to be 1. Right? Okay, look to this matrix now. Look to this matrix. We have leading entry here. Everything below it 0. We have leading entry here, above and down zeros. And we have a leading entry here, fortunately, without doing anything. And we found that everything from the left is 0. Okay? Okay, now this is the leading entry, but there is something else that we need to get rid of these to be zeros. We want this to be 0 and 0, right? So we need to make some row operations. So we can get this into easily. Actually, the first thing is looking to this half here. So if we are going to multiply row 3, okay, by minus half and add it to row 1, then we're going to get this to be 0, right? So multiply minus half times 0 plus 1, okay, it is 1. And minus half times 0 plus 0, it is 0. And minus half times 1, it is going to be minus half plus half, it is going to be 0, right? Okay. Now let's get rid of this minus 3 over 2 to make it 0. How? Simply also. We are going to multiply the row 3 by 3 over 2 and add it to row 2. So now multiply 3 over 2 times 0 and times 0, it will be the same here, 0 and 0. And 3 over 2 times 1, it is 3 over 2, plus minus 3 over 2, it is going to give us 0 here. So we got rid already from these two elements by elementary row operations to make them zeros here and here. Okay, so now this is 0. So we have leading entry here 1, 1, and here 1. Right? And if you look deeper, you're going to find that we reduced it to what? Exactly to the identity matrix. So this is a reduced matrix that is row equivalent to C. We call it row equivalent because we have done some row operations, having been obtained from it by a sequence of elementary row operations, as you have seen. Okay, elementary row operations, as you have seen. In this example, we started with C and obtained a reduced matrix. If we had used a different sequence of elementary row operations, what is the meaning of different sequence? Means that instead of starting with this row, we can start with this row, or instead of making this element to be 0, we can start with this to be 0, or vice versa. That's the meaning of another sequence. Okay, so the sequence of the steps for the elementary row does not matter. Okay, if you can do another sequence and you are going to end up with this elementary row, it is okay, you can do it, no problem. Different row sequences will not make any change if you are going to get the final reduced form. Okay, so the answer, could we have reached the different reduced matrix? The answer is no, as you can see here. It means that any sequence of elementary row operations will bring you to the right end reduced form. Okay, now let's go to put a kind of theorem. It is straightforward theorem. Every matrix is row equivalent to a matrix in reduced form. Okay, so if we have a matrix, it is going to be row equivalent. Row equivalent means that the reduced form is going to be obtained from some elementary row operation. This is the meaning of row equivalent. Okay, so if we have A and we are going to make some row operation O1 and O2 and O3 and so on until we reach AR. So we call this AR is row equivalent to the original A. Further, the reduced form of a matrix is completely determined by matrix itself, not by the reduction process. Yes, this means that we are making the process on A. So if you are going to make some operations, row operations O1, O2, O3, and I will make another type of operation which is different than this O1, okay, it is going to be another 1, O2, O3, which is different. This one is different than this. You go with this procedure, I went with this procedure, and we both can reach the same reduced matrix. That is, no matter what sequence of elementary row operations is used to produce a reduced matrix equivalent to A, the same reduced matrix will result. Okay, it is simple logic and no problem with this to be understood. Okay. Now let's go to the steps of the solution for obtaining the reduced matrix. First, move any 0 rows to the bottom of the matrix by row interchanges. This is first rule. Second, then start the upper left leading entry, and by multiplying this row by a scalar, obtain a matrix having a 1. This is the value of 1 in this position. And number 3, add multiples of this row, which is the leading entry. Okay, if you have, like, for example, 1, 2, minus 2, and this is the leading entry, for example. Okay, then already, and this is 0, 0 here, for example, then this row already it is qualified. Then use it if you want to get some other zeros underneath. Okay, add multiples of this row. Okay, this row means that from the previous step. to the other rows to obtain zeros in this column below this leading entry. Okay, that's very important step. Okay, that's it. These are the main 3 steps to get the reduced form from any kind of matrix. Then move to the second row and carry out, then go to the second row and carry out the same procedure, which is the same 3 steps again with its leading entry. After each non-zero row has been treated, a reduced matrix results. Okay, so this is actually summarize to you what you are going to do in order to obtain the reduced matrix. Okay, now it's very fine now. Now let's go and have some examples, and you are going to realize that it's straightforward and easy to be formed. Okay, now the first example is reduce this matrix. We have a matrix here. So before doing any actions, you need to look to the matrix. Looking, first of all, the first step was, yes, 0 rows. Look here, we have here this row. All the elements are zeros. Then it should go where? Exactly, we should put it down. Okay, we should put it at the bottom of the matrix. We should put it in the bottom of the matrix. Okay, now let's go and see what we're going to do. First, interchange rows to move the 0 row to the bottom of the matrix. So this 1 is going to be moved here, interchanging it. Okay, and we are going to move, okay, this row, for example, we are going to put it instead here. So it comes here, 0, 0, 2, 0, 0. Okay, now this is the case. This means that as if that we shifted all of them up. Okay, we shifted this down, interchange, and shifted, give them shift up, all of them. Okay, now the leading entry of row 1 in the 1, 3 position, okay, the leading entry of row 1 is in the 1, 3 position. 1 here, this is row 1, and this is column 3. So this is the leading entry of row 1, 2. It seems not to be good. We want it to be what? Exactly 1. Okay, so and the leading entry of row 2 is in the 2, 2 position. Look here, we have the leading entry of the row number 2 in this position, which is 2, 2 position. Do you remember the rules or the conditions? This is not good. It seems that it is better to flip it, or to exchange, or to interchange these 2 rows. This should be in the first row, this should be in the second row. So we want the leading entries to move down the matrix from left to the right. That's right. So interchange rows 1 and 2 to obtain. We're going to change this. So we are going to obtain, yes. So now we are interchanging this row 1 and row 2. So we are having now here this 1, it comes here. So it is going to be leading entry for us. And the second row, still the leading entry here is 2. Okay. First of all, before going afterwards, it seems that we are having leading entry 1 at row number 1. Then, and look down, all of them there are zeros. So it is okay. Now this is the leading entry for row 1, and row 1 is qualified. Look to row number 2. We're going to find that the leading entry is 2, and this is not good. We need it to be 1. So we're going to what? Multiply it by 1/2. Okay, so multiply row 2 by 1/2, and you are going to obtain this matrix, which is 0, 0, and instead of 2, it is going to be 1 and 0, 0. That's it. Okay, so now we have the leading entry for row 1 here, and the leading entry for row 2 to be here. Okay, look up and look down. Up is zeros, and down it is 0 here, but 3. This is the 3 here. So we need to get rid of this 3 and make it what? Make it 0. So what we are going to do, we are going to get benefit from this row 2. as we said, we are going to add multiples of this row to row 3. So we're going to multiply row 2 by minus 3, and then we're going to add it to row 3, right? So multiply here 0, 0, so this is going to be zeros, and minus 3 times 1 plus 3, it will be 0 here, okay? And then there are zeros, so these elements are going to be the same. Let's see this operation, the next slide. So in this, so we're going to, yes, this is 3. We're going to, exactly, we're going to multiply, add minus 3 times row 2 to row 3. Then this is going to be zeros. The two first elements are going to be the same zeros. Do not worry about them, because above them there are zeros. And then this turned to be 0. And then here, 0 and minus 4 would be the same because we have zeros here. So they are going to be the same for row 3. No addition from this row. Okay. Now we are looking back to this, the whole matrix. We have 0 here. Under it there is zeros, 1 here, and leading entry 1 and zeros. And this is the leading entry 1. Above it zeros, below it zeros. So it qualifies now to be in the reduced form. Look to the row number 3. You are going to find that the leading entry is minus 4, and it's the end. So this is not good. Yes, exactly. We are going to multiply it by minus 1 over 4 to make it 1. That's it. So this minus 4 is going to be changed to be 1 by multiplying the row 3 of the matrix by minus 4, and then leave it as it is. So now we have row 1 leading entry, row 2 leading entry, and then row 3 leading entry 1. Then we should look above and look below. Below no problem because it is zeros here. And above there is no problem in this element, it is 0, but here that's the problem, which is 1 here. We need to get rid of it and make it 0. How we can do it? It is easily. We are going to look to this row 3. We multiply it by minus 1 and add it to row 1. This is what we are going to do. Multiply it by minus 1. So minus 1 times 1, it is minus 1. Plus 1, it is 0. That's it. So this is what we are going to do here. So this is 1 multiplied by minus 1 here and add to this. This would turn out to be 0. Okay. Now we are in the reduced form. Our matrix is going to be 1 here, 0 above, 0 below, and we have 1 here, 0 above, 0 below, and we have here for row 3, 1, 0 above, 0 below, and we have the 0 row here at the bottom. This is considered to be AR, or reduced form. This is considered to be a reduced form. This is considered to be a reduced form for us. Okay. If we had reduced A by using another sequence of elementary row operations, we would have reached the same AR. So if you try to play with the elementary row operations by any kind of sequence, you are going to reach at the end to the reduced matrix. Okay, the sequence of row operations does not matter. Okay, that's what we want to understand. Okay, now let's go to a theorem that is important for us to know and would give us more insight. Let A be any matrix, then there is a matrix omega such that omega times I equal to AR. Here we are going to talk about something that is very nice, that if we are going to have A, which is a matrix, and we want to get the reduced matrix, which is, let's give it this notation, which is AR, we are going to make a lot of row elementary operations until we reach AR, right? Okay. We claim, or this theorem is claiming, that instead of making these row operations, which is long, we can multiply a magic matrix called omega by this A, and it would give us directly AR. Okay, that's the point. So this is what we call it, the magic matrix, which is matrix. As you are going to see, it is going to be formed. Actually, it is not out of magic, but it is going to be formed by the same steps that we have had. Okay, so the point is, we are going to, instead of the point, what we are going to do here, it's like a verification for us, that we are going to augment the original matrix. Augment means that the matrix, which is A, we are going to add some columns to the right of the matrix A, and this, if the matrix, for example, A, it is n by m, then we are going to add to the right of the matrix the identity matrix. So we're going to put here like dashed line like this, and we are going to put in here, and this, we call this is the augmented matrix. And then we are going to go with all the elementary operations again until we reach AR, which is the reduced matrix on the left, which is from A. And the reduced or the row operations on the identity matrix would give us exactly omega. It would give us omega. Okay? This is actually the explanation of this part, what I've said now. Okay? So we are going to make or form the augmented matrix, which is going to be the original matrix on the left, adding to it A and IN to the right. IN is what? Take care. IN, it is here, it is the identity matrix based on the number of rows of the original matrix. Then we are going to make the original row operations, the ordinary, the common row operations, in order to obtain AR. And with the same row operations being done on A, it will be done on IN, the identity matrix. We're going to realize that omega, which is formed from the identity matrix, is going to be the omega that we are searching for. Okay? That's it. So let's understand it through an example, and you are going to understand my point. Let's assume that we have A. As you can see here, this is a 2 by 3 matrix. Number of rows, 2. Number of columns, 3. We will reduce A, and at the same time, we're going to find the omega matrix. Okay? So take care that we are going to augment this matrix by IN. In this case, it is going to be I2, which is 2 here. This means that we are going to have 1, 0, 0, 1. This is our matrix, identity matrix here. So we're going to put the original matrix here, and we're going to put dots like this. Dots means that as if that we are expanding our original matrix, and we're going to put the identity matrix 1, 1, and 0, 0, as you can see it here. And we're going to call this as A dot I2. Okay, this is the augmented. We call it the augmented matrix. Okay, so this is the first step. What should we do after that? We're going to go with the row operations to reduce this matrix A. So this is here the matrix that we have, augmented matrix. We are going to make some row operations to make this reduced. First of all, this is minus 3. We want it to be 1. So we're going to multiply by minus 1 over 3 times row 1. So we are going to have it 1 here. Okay, and multiply, of course, all the row, including the identity matrix, by minus 1 over 3. So it will be minus 1 over 3 and 0 here. And then we are going to, this is what? This is 4. Looking up, looking down, then we need this to be 0. Now we understand exactly. We are going to multiply this row by minus 4 and add it to row 2. And this is what we are going to do here. Add minus 4 times row 1 to row 2. Then you are going to get here 0. So this is 1, the leading entry. Here it is 0. And then you are going to find that everything is going to be multiplied This is minus 4 times this row and add it to this row, to row 2. Then you are going to find that the identity matrix is being formed with you. It is being formed based on the elementary row operations that we are doing. Then still look to this second row. Where is the leading entry? It is minus 2 over 3. So we need it to be 1. What we are going to do? Multiply it by 3 over 2. Okay, minus 3 over 2. Multiply it here and you are going to find that it turns to be 1. And then do the same for the remaining elements, including the identity matrix. Now look to this element. It is leading entry of row 2. Look above, non-zero. Then we need to make it 0. How? Exactly. We're going to multiply this 1, which is row 2. We're going to multiply it by 1/3 and add it to row 1. Exactly. Here we have 1 and adding it to row 1. Then you are going to find that this turned to be 0, and then these elements are going to be changed accordingly. Then we have here, this is the I-reduced elementary, leading elementary, the leading entry. It is 1 and then 0 here and then 0 here. Then this is considered to be the AR. In this case, this matrix is going to be omega. It is going to be omega. How we are going to be sure of this? We're going to make the multiplication that we have said, that AR, that already we have obtained from the previous slide, and this is omega. We are going to multiply omega by the original A. So we're going to multiply this omega by the original A. It must give us AR. It must. So now get this omega, which is this omega times A. This is omega from the previous slide times A. Please multiply these two. You're going to find that it gives you the same answer of AR as we have obtained from the previous slide. Okay, so let's go here. This is AR. Yes. We have this. This is AR, which is this one. Okay, so now this is the way, and this is the reduction of the elements or the matrices, and this is the theorems that we need to understand. Now we are ready now to go to the in-class assignment, I guess. So in our in-class assignment, as usual, you are going to look to the example or the assignment and stop the video, and then you are going to work out the examples or these problems by yourself without looking to any other sources, and try to solve by yourself. If you are going to make mistake, no problem. You're going to find the solution and rectify your solution and understand and repeat it again until that you solve it correctly. So in class assignment, find the reduced form of A and produce a matrix omega such that omega times A equals to AR. We have 3 different matrices. Okay, you can have a look on this. There's keys here, only key for you. You can see that there is 1 here. It is very nice for us, so no need to make anything. Here for the second row it is 1. It is very good also, but the problem is here there is not -1, so we need to get rid of this to be 0. So the point is, multiply this row by 1. It is nothing here, only by 1 means that adding this row to this row, you are going to get this 0 and continue after that. Here, this 3 needs to be multiplied by 1/3, and it will be turned to 1, and here it is 0. Then it will be the leading entry here. 1, fortunately, it is 1 here. Then we want to get rid of this 1 after being multiplied by 1/3. Then you can proceed with this. Here, the first thing is what? Exactly, these 0 rows. Not get rid of them, just put them down. That's it. So shift them down and bring this 1 to be in the second row, for example, and make the row operations to get the reduced form. Okay? Okay. Make the assignment and come back again to the video. Okay. Now welcome back to the video if you have done what I have said to you. And these are the solution. This is the quick solution. Okay, this is the quick solution. If you have done the row operations, you're going to find that omega is going to be the identity matrix and AR is going to be in this form. So check your results. Okay, the detailed solution of the problem A is going to be seen here. You can look to it. Okay, I'm not going to explain it in detail, only I'm going to give you hints. You can look to it from the PPT file. So we started with A, and then we make the augmentation. We put the identity matrix here, and this is A as it is. Then we are going to, we are going to put the, we have here, this is the leading entry. Then we want this to be leading entry, and we want to get rid of this. So we're going to have R2 plus R1 to make this to be 0. Then we have leading entry here, and this is zero row here. And this elementary or this identity matrix is going to be formed. So in this case, AR is going to be this matrix, and this omega is going to be the formation of the identity matrix, and then multiply for verification. And this is what you're going to do also in your homework. Multiply omega by A to check that it equals to AR at the end. Okay, so this is the detailed solution. You can stop the video and you can watch how the flow is. For the second problem, as I said, the hints that you are going to give, you are going to find that omega equals to this matrix minus 3, 0, minus 1 over 3, 0, and minus 1 over 3 and 1. So please check your results if you have obtained it right. AR is going to be this form. AR is going to be for this form. So let's go to the detailed. This is the detailed solution. You start with A. Make the augmented matrix I2, put it with the form. So we're going to put dots here, and this is I2. Remember, it is 1, I2. It should be I2 because we have here 2 by 4. So our identity matrix is I2. And then make the rows operation based on what I have explained in the video. Okay? Then you're going to end up with omega on the right hand side of the augmented matrix, which is going to be here, and this one is going to be AR. So here this is AR, this is going to be omega. Okay, so that's the case. Please check what you have done. This is AR. Okay, for the third solution, for the third example or the third in-class assignment, you start with A. Make the augmented matrix as it is. We have here 1, 2, 3, 4. So we have like 4 by 1, 2, 3, 4. It is 4 by 4. Then identity matrix is going to be I4 based on the number of rows. So we have this is the identity matrix as you can see here. 1, 1, 1, 1 on the diagonal. Make all the operations. Okay, you can find the details here. Please do and work it by yourself. It's important for you. Okay, then you are going to end up with something that is the 2 zeros here, 2 0 rows. We can find them at the bottom as we said. The same also you are doing on the identity. Everything that you do here, you should do on the identity matrix. Then you are going to end up with this is AR, this is omega, which is on the left, this is AR, on the right, it is omega. And then make the final check omega times A. You are going to find that it gives you the same AR that you have started with. Okay, this is the in-class assignment. I hope that you have worked it well and you can find the details. If you stop at any point, please go back to the detailed solution and you can find what problem or what mistake that you've done. Now you are ready to have the home assignment. The home assignment. So these are the problems for the home assignment 1, 2, and 3. So find the reduced form A and produce a matrix omega such that omega times A equals to the reduced form, as we have done in the in-class assignment. You have three problems here. Okay. Okay, thank you very much for listening, and see you in the next video.